So my name is Richard, and I've been lucky to be here over the last few months and to work with Lucia and Shai. And we've been working on this idea of taking existing merger trees from n-body simulations and scaling them to different cosmologies. So I'll tell you a little bit about that. So the context is, I think, clear. So today we have this era of precision cosmology. Observations are going deeper, both into higher redshifts and nonlinear scales. And so we really need better galaxy formation modeling than some simple halo occupancy distributions and so on. Unfortunately, at this point, often what happens is that a likelihood is intractable, both because of galaxy formation and also because of survey systematics. So at this point, machine learning has become a nice tool to extract information from these data sets. But it comes with this downside that you need thousands of simulations. Of course, there's CAMELS, which has many thousands of simulations, but they are all quite small. So in this context, there is this something in between of empirical approaches and hydrodynamical simulations, as semi-analytical modeling. And the idea is that we can run many and bigger n-body simulations from which we can extract dark matter merger trees. Now, these merger trees will track how halos and structure assembles in lambda CDM. And then on top of these merger trees, we can track galaxy evolution through a set of differential equations. So this means that it's very fast to evaluate once you have the trees from the n-body simulations, and you can explore your parameter space and also scale it to much bigger volumes than you can do with hydrodynamics. So a leading effort here has been done by Lucia with this CAMEL-SAM suite. And so this is 1,000 n-body simulations. All are varying cosmology. So this is all lambda CDM, varying omega matter and sigma 8. And then all of these simulations have been pre-processed to generate the merger trees from them with Rockstar, and then run through the Santa Cruz semi-analytical model. And within all these 1,000 simulations, what is also varied is the astrophysics. So things like the supernova feedback, AGN feedback are all changed. So this is good. But thinking a little bit into the future, now we've had 100 megaparsec boxes, and the total cost was maybe 8 million CPU hours. The surveys that we have now are much, much larger than 100 megaparsec of range. And so what you would like to do is model galaxy formation over bigger volumes self-consistently. And so one can think about it very quickly. And if, for example, you wanted to have 300 megaparsec of range boxes at the same resolution, such that you can still resolve the merger trees, each simulation would be maybe 250,000 CPU hours. And to do 1,000, you would need 250,000,000 CPU hours. So here we thought maybe we should take a break and think what could be the solutions. So of course, the obvious one is to use some machine learning approach to emulate n-body simulations and generate things very cheaply. The second thing is not to use machine learning and take advantage of this cosmological scaling, which I will tell you about now. So here the idea is that I can run a few expensive n-body simulations, and then I can take a simulation and map it to a different cosmology than the one with which it was run. So for example, I can change the underlying omega matter or sigma 8, which controls the matter density or the fluctuations of the matter field. And how this works is that it's very simple. All I have to do is I need to find some scaling of length and target redshift to which I map my original snapshot, such that across a range of comoving scales, the linear matter fields have similar variances. So this is this optimization problem where these are the variances. And I try to choose my target redshift and the length scaling such that this is always on the order of 1. And once I have done that, to transform my snapshot, I just have to multiply the particle positions by a simple scalar factor, and similarly for the particle masses. So this is very simple. And this is an example of two simulations. They look almost identical, but actually one of them has higher sigma 8. It's a bit difficult to see by eye. But if you plot the power spectrum, you can see, as you would expect, the one with higher sigma 8 has consistently more power across all scales. So this is at redshift 0. And now what I want to do, I want to take a snapshot of the simulation with lower sigma 8 and scale it to be at the cosmology with higher sigma 8. And so all I do now, I multiply the particle positions by the scaling factor, and I move them to a different redshift. And after I do that, I have this decent agreement. So on linear scales, it agrees basically by construction, because that's how I choose my mapping. And there is some little disagreement maybe on the nonlinear scales, which has to do with corrections within halos, but we can correct for that as well. So now that was how to treat if I have a particle snapshot. Now, we don't want to work always with particle snapshots because that can still be expensive computationally. So the idea is to take an existing halo catalog and scale the halos directly to different cosmologies. So at this point, it becomes a little bit more complicated, a little bit more messy, and we introduce some empirical corrections, which basically assume that the halos are roughly on average described by an NFW profile, and then we can derive these corrections. So what we can correct are some masses, concentrations, velocity dispersion, and these may be other things, but this is what we need for the semi-analytical model. And so now the final step is how to actually treat the merger trees. So what we can do is we can scale all the halos in a simulation and just simply assume that the connections of halos in between snapshots remain the same. So the example is here. I have some original tree, which was run with a higher sigma 8. I extract it from the n-body simulation, and then I want to scale it to a lower sigma 8. So a very simple assumption. I assume the tree, the morphology of the tree, remains the same, and I just change the halo properties. So for example, I think in going from higher to lower sigma 8, I would lower the masses a little bit, and everything would shift a little bit into the future. So in practice, how does this work? So this is an example where I have two n-body simulations. I match their initial conditions such that in both simulations, I can identify the same halo, and then I evolve it with a different cosmology. So this would be one with lower and one with the higher sigma 8, and then it's the blue and the green. So the halo with the higher sigma 8 is growing a little bit faster. So this is the mass as a function of time. And then what I do is I scale the merger tree of the original halo at the lower sigma 8 to the higher sigma 8, and I see they match super well. And this can be also extended to different properties like the concentration, and again, there's a good agreement. So this is an example of a single halo and showing that I can match the mass accretion histories. Now, this was a single object. Maybe I picked a lucky one. So this is what it looks like if I do this comparison for many pairs of halos. And this is, I am now only showing mass and concentration. And it seems that in all cases, the bias is maybe in mass on the order of 1%. There is some random noise, but anyway, if I compare the masses of the scaled halos to the masses which originate from target n-body simulations, it's always about the same, within 1–2%. The concentrations are a little bit more difficult, but nevertheless, it is agreement to within 5%. So this is good, which means we can scale the halos and be fairly confident in their properties. So then the next step is to check some other summary statistics of the halo population. So here, for example, I'm showing the halo mass function. So these are the original halo mass functions of my simulations. So before scaling, because it's different sigma 8 in the simulations, there are some differences. So the one with higher sigma 8 is a bit higher on the high mass end, and then a bit lower in response at the low mass end. So now I scale all the halos in the simulation, and I get this agreement. So this is nice. By eye, it looks good, and there is no longer any systematic bias. So great. I can scale the halos. I can scale the merger trees, and I'm quite confident that there's nothing going terribly wrong. Now, the next step is to take the scaled trees and run the semi-analytical model on top of them and see whether any errors that we have due to the scaling algorithm are significantly reflected in the galaxy properties. And so this is what it looks like. At first, you see this x-axis is index. So now suddenly it seems it's no longer 1–2%. It's huge differences. So this is where I take one simulations which are scaled, and then I compare it to a target simulation, and I plot the differences in stellar masses, H1 masses, and black hole masses of individual galaxies. This was a little bit worrying at first, that it seems to work for halos, but it suddenly fails terribly for galaxies. But the next exercise that I did was to take the same trees that I input into the simulation and change the random seed of the galaxy formation model. And this produces that distribution, which this one is a little bit broader, but actually most of this noise originates just from the stochasticity of the galaxy formation model. And most importantly, these galaxy masses, they don't have any systematic bias going in either direction. So the next step was to look at some summary statistics, this time of the galaxy population. And when I was looking at the stellar mass functions, again, I am able to match them. So I was changing cosmology of my scaled simulation from sigma 8 of 0.8 to 0.9. Of course, I can also change omega meta or other cosmological parameters. So stellar mass functions match. Star formation registries match as well. I looked at, I don't know, H1 masses, black hole masses, and so on without any problems. So this is all good. Now, that means that all the galaxy properties, they look similar, and I don't seem to have any significant error. And so what about if I give this to machine learning? Can it actually tell that one of these trees, or some galaxies originate from scaled trees? So the exercise was I wanted to train some machine learning model to predict sigma omega meta and sigma 8 from simulated stellar mass functions. So the training set does not have any scaling in it. Now, I give it a pair of unseen data. One comes from simulations, and the other one is coming from a scaled merger trees, which I ran through the galaxy formation model, and I generated the stellar mass function. So that's here, and okay, by eye they look the same. So what happens? It's all perfectly consistent. So the gray is what I get from the simulated test data, and red is what I get from the scaled stellar mass function, and there are no problems. So okay, again, a single example. So maybe there could still be a systematic bias hiding somewhere. And so that's what we did here, is where I trained the machine learning model on the simulated data, and then I can test it either on Camel-SAM test set, so test set of the simulations, or I can test it on scaled simulations, which have never been used during the training. So in principle, if something went wrong, the green, so the scaled data, could be out of distributions, and you would recover a bias in the underlying cosmology, but that is never the case, and this works super well. So here I have an example when I do mapping from stellar mass function to cosmology, but it works very well for galaxy clustering with 2-point correlation functions as well. So then I can ask, if I wanted to do cosmological inference with something like Camel-SAM, how many simulations would I actually need to go from stellar mass functions to cosmology? So the idea here is that we have some 2D parameter space of omega meta and sigma 8, let's say, and I choose how many simulations do I need to populate this. So here in this example, I have a single box, and the color indicates sort of the direction along which I can scale it to get the least errors in the power spectra. So the first thing that I can think of, that I can try is, let's say that I have 50 n-body simulations here, from which I generated my merger trees, and I use it to generate 1,000 scaled simulations. So in principle, each of these original simulations can be reused up to maybe 20 times to generate the scaled simulations. And I can compare it to the fact where I have 1,000 n-body simulations. So the second case is much more computationally expensive. And this is what it looks like. So this is the true against predicted omega meta. And again, by eye, it's consistent. Doesn't seem like there's any significant bias. So to make this a little bit more quantitative, I had a look at this. So now this point is the root mean squared error, where I generate 1,000 simulations from 50 original simulations. And now I can increase this number going all the way to 750. And I compare it in red is the one where I had a suite of 1,000 n-body simulations to train on. And the root mean squared error, maybe there's some mild evolution, but roughly it's all consistent. So it seems that even 50 simulations are consistent to get good cosmological predictions from the stellar mass function. Now, of course, this is the root mean squared error. I want to also predict uncertainties. And so that's the second plot. And it seems that when I only have about 50 or 100 simulations, the model becomes a little bit conservative. The errors are largest. And then quickly already, once you have about 200 simulations, it settles down and you don't gain any benefit. So it seems if you wanted to map stellar mass functions to cosmology, 200 simulations and 1,000s would be more than enough. So, and all this works even if you have galaxy clustering, so through 2-point correlation function. Okay, so in conclusion, we now have a pipeline to scale a set of existing merger trees to different cosmologies and then run them through the semi-analytical model. And this is fast, so on the order of, it takes maybe 8,000 CPU hours to generate a new n-body simulation. We can do this in 2, 5, maybe 8 at most CPU hours. So I can generate these thousands of simulations very cheaply to the point that it's almost negligible. And I have validated this against stellar mass functions or two-point correlation functions. It seems to work. I have looked at other galaxy properties, and again, there is no systematic bias. And so as for the future, what we're thinking about is how to do much larger cosmological inferences. So while previously within CamelSAM there was 100 megaparsec over H boxes, we would like to do it with larger boxes, so maybe 200, 300 megaparsec over H, at which case we can only generate fewer. We can generate fewer of them, and then we can use the scaling to populate the parameter space more densely. And the second step that we're going to be working on is to turn this into a differentiable rescaling algorithm, such that I can take the existing tree and compute gradients of it with respect to cosmology like omega meter and sigma 8. Thank you.
Questions for Richard? Yes.
Really nice talk. Could you just really quickly summarize like how you figured out how to do the scaling again? I think I lost a detail there.
So this goes back to Raul Angulo back in, 2009, and then the Baco team.
Yeah.
And so what you do is you have an original snapshot,
Yep.
and you can compute the linear variance with some filters of certain comoving scales, right? So this, and then you want to find, you have a target cosmology to which you want to go, and you want to find at what redshift this target cosmology has the same linear variance across a range of scales.
Yeah.
And then you also play around with the length units.
So these like parameters have to themselves be tuned to some set of simulations. Is that right?
No. No.
It all comes from the theory?
So because so the linear variance comes from the linear power spectra.
Uh-huh.
So you don't need any tuning.
Even for the choice of length scales?
No.
Okay.
So no.
Okay, interesting.
All you need is you need to know what is the linear matter power spectrum. That's the only input you need. Of course, you could choose to use the nonlinear power spectra, which are a bit more difficult to get.
Okay, thanks.
And do we have another? Oh, Jared?
So just to make sure I'm understanding, you're applying these to sort of trees from n-body simulations,
Yes.
right? So if they're dark matter only or pure gravity, then gravity is more or less length, scale, invariant. And so I think this all makes sense. But in modern cosmological simulations, there's often a lot of dust, gas, various kinds of physics, radiation, all of which do maybe introduce length scales into the problem. Do you think this method would be applicable to that framework, or is that something that needs a lot of testing, or what's your intuition there?
I would be very careful about that. I'm confident that it works well for dark matter only simulations. And then the advantage of SAMs is that we can run them cheaply on top of it. With hydrodynamical simulations, maybe it would work on large scales, but definitely not once you go to galaxy scales.
Any other questions? You in the back?
Hey, Richard. Can you just help me interpret the implicit inference results that you were showing here?
Okay.
Does doing this get you, allow you to run 20 times less simulations than you needed, with raw things, or 5 times? How much more efficiency are you getting at?
Well, this is what we're getting into properly now. But in principle, I mean, if you can, for example, accept that your errors will be a little bit larger, then you could do this inference with stellar mass functions with only 50 original simulations. So we're quantifying this also from the point of view of two-point correlation functions. If, for example, here I had, 10 n-body simulations distributed across the space, and I'm seeing that once I have 50, 100, I get a reasonable inference, which is comparable to having 1,000 simulations.
do you think that you could choose those 10 simulations in smart areas of parameter space that don't overlap along this degeneracy here?
You could. Yes, that is something that we're thinking about. So at the moment, the simulations are spaced randomly, which is maybe not optimal. So what often happens is that you want to have your simulations at large values of sigma-8. So what we have done already is to put, I don't know, maybe 10, 20 simulations at sigma-8 of 1, because it's always easier to scale towards lower sigma-8. So there is something that you can play around with the placement of simulations. But also what I think would be more interesting is to do this in a way of active learning. So that's, let's say that at first you run 10 simulations, and okay, the errors maybe are still a bit large because you need to take large steps in cosmology. But then you get a better idea of where your posterior is, and then you start generating more n-body simulations there.
Thanks.
All right, let's thank Richard again.